All right, so your homework was to read through the intro section of the assembly language stuff there. So we would be ready for a quiz, right?
Yeah.
So are we ready for a quiz?
Yeah.
All right, well, we're not going to have a quiz.
Yeah, you're right.
60% of the time, it works every time.
Okay. But hold on. We are going to discuss stuff from it.
It was a poorly worded.
Yes. In the reverse,
Super poorly
the
worded.
reverse is not reverse, it's inverse.
Yes. I got some qualms, let me tell you. They said to make a negative number, you reverse the bits. Okay? So I'm like, you put the 0 here, there. You put the 0 here, there. You just.
I mean, it's fair enough. Yeah. That would be reverse.
Yeah.
Yeah,
I reverse a number. I don't go the opposite.
Yeah, right. Yeah, I usually say flip all the bits.
Sure.
Yeah.
I would.
So you just take the.
So you're talking about 2's complement, right?
They didn't say that.
Yes.
For taking the negative number.
Yeah.
Okay, so here, while I'm bringing this up, why isn't this on?
I don't know when you turn it on.
I did turn. You saw me push it, right?
Yeah, sure. Yeah.
It's on. 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 Are you still pressing the button?
No.
It's like flashing.
I see light. I see light now coming off this thing.
Okay, now it's solid.
Ah,
I can see it.
all right. Do you want hit the second from the top button on the light flippy thing there? Not the top one, the second one on the top. Oh, look at that! Boom. You see how much better you can see this now? All right. So tell me tell me about 2's complement first. You read about 2's complement, right?
It didn't. I don't believe it used that term.
All right. So tell me about binary subtraction. You talked about that in it?
You just add negative numbers.
All right, so you need to get the negative number version of a positive number, right? And how do we do that?
Reverse the bits, apparently.
Okay. All right, so they had to have called it 2's complement.
They did.
Yeah, so you just didn't read it.
I did read it. I remember seeing complement in there. Is it bolded? All right, it might be.
All right, so tell me about, now that we've decided that it's in there, tell me about 2's complement. What's the purpose of it? We already said. So it takes a current positive number and makes it its negative equivalent. And how do we accomplish 2's complement? What is the process of getting the 2's complement of a number? Go ahead.
You take the reverse, which we figured out is really the inverse, and then you add 1.
Okay. Let's see. Am I in the right section? What section? Intro. Previous. Oh. Whoa. Everybody relax. Okay, let's go down. Well, so we'll kind of look at this. I want to bounce back and forth between assembly and kind of our book things, but we'll talk about it. Okay, so you take a binary number, you flip all the bits, and you add 1 to it. And that gives you the negative equivalent of that number. So if we had the number 5, for example, let's kind of come down here. Where do I want to?
Do you have a link to the PowerPoint?
I do, but I haven't put it up yet, but let's go ahead and do it right now while I'm thinking about it. Well, since you reminded me. Copy, don't allow editing because you guys will screw with me. All right, and then I should be able to go in here. Web link, course slides. All right, so you should have that now. And then let me go ahead and do the lectures. Okay, so now you have all those things. All right, so let's just jump down to, we'll just go right here. So 2's complement, is that spelled right? Nailed it. All right, so if we take the number 5, what's the binary representation for the number 5?
1, 0.
1, 0, 1. So 1 in the 4's place, 0 in the 2's place, 1 in the 1's place. Okay? So that's the number 5. To get the 2's complement of that, i.e. to get the number -5. So this is 5. -5 would be flipping all the bits. So a 0 becomes or a 1 becomes a 0 becomes a 1 becomes a 0, then you add 1 to that. So this would be -5. Make sense?
So technically, you just take you switch all of them, but the ones place.
Well, no, you switch all of them, then you add 1, because if you have a 1 in the 1's place, then you're going to you'll have carry bits.
Okay.
So for instance, the number 4 would look like this. Then it would be 0, 1, 1. Then you're going to add 1 to that, so that's going to be 0. That's going to be 0. Actually, hold on. Let's actually do the math there. That's 0, 1, 1 plus that. 1 plus 1 is 0, carry the 1. So the answer here would be, here, let's just give you placeholder 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. Then this 1. Oh, yeah, it is. So that is 4 and -4. Now you might say, okay, well, how can that same thing be both? We have to know that this is in 2's complement form. That make sense? We have to know that it's in 2's complement form.
Then isn't the idea if I want to subtract 4 from something, I add that number to whatever I want?
Yep.
Isn't that doing the same thing as adding 4 to the number?
Same thing as
So
adding
would
4
it
to...
be
Like,
like
those
those was 8?
So if I want to say 8 minus 4, okay, I do this, and now I do 8 plus -4, which
Yep.
is the same thing as 4. How does that not come out to 12?
Well, okay, so let's do the math.
Yeah.
All right. So
I'm curious to see how
this is 4. This is -4. So the plan is it should be a 0. Right? They should cancel each other out. All right. So 0 plus 0 is, I'm just going to give myself placeholders there for my bits. So 0 plus 0, we're starting on the right, is 0, no carry. 0 plus 0 is 0, no carry. 1 plus 1 is 0 with a single carry bit. So this is called an overflow. This is the value 0.
So we didn't get to expand to the 4th. So
Not in this case.
can you do 8 minus 4 for me then?
Sure. So the reason I'm introducing overflow bits, I don't think that was in your
I think it
tutorial.
said something about overflow bit.
So when we get into assembling language, there's a specific register that handles carry bits. Okay, so the point is that from your perspective, there is a 1 there, right? But do we treat this 1 as part of the value, or do we treat this 1 as part of the overflow bit of it? So this would be the 1's place, the 2's place, the 4's place, the 8's place. So there's an 8, which would be equivalent to 4 plus 4, not 4 plus -4. So we had to have knowledge that this guy was in 2's complement form in order for this to work the way we wanted it to work.
So had we been adding 4 plus 4 there, it would have been 1, 0, 0, 0. It wouldn't have done the overflow.
4 plus 4. Okay, so if we assume this guy was not
So
in
you're
2's
saying
complement,
because we're 2's complement,
the overflow disappears. Yeah, because it's in 2's complement. Yeah, we have to know that this is a 2's complement representation of a number in order to work with it. All right, so punchline with 2's complement is, why does it exist? What's the why might we have something like 2's complement in existence? Why not just subtract? Go ahead.
So the machine can do subtraction?
Okay, but the machine's not using subtraction.
So that the machine doesn't have to worry about all the positive numbers and negative numbers?
Okay. So the reason, I mean, we're doing arithmetic here, right? We're either adding numbers or subtracting numbers. These are, from a human being's perspective, these are considered fast things, right? It's not that hard to add and subtract. Which is harder? If you had to choose, okay, so from a human being, maybe our feeling is subtracting is a little bit harder than adding. Adding is kind of a really easy thing we do pretty often, or something like that. Even if it's close, it's not unreasonable to make that statement. Now, last time, we were talking quite a bit about hardware. So we talked about our CPU being a collection of circuits. Now, what's a circuit again? What's the purpose of a circuit? Okay, so we kind of compared a digital circuit to kind of being like a program, right? These guys are sort of the same thing. Over here, we have software that we've written that has a spill-through effect where we drop our inputs in, kind of like Plinko in the show. Let's Make a Deal or Price is Right, one of those two. Your input drops through all this logic until you finally get an output. We can build that in software over here. No harm, no foul. Or we can also build it in hardware, and that's what a circuit is. So we provide input to the circuit. It goes through various logic stuff, the hardware equivalent to if statements and that kind of stuff, and it ultimately gives us an answer, an output. Make sense? Okay. Now, why would we do something in hardware versus software? I mean, we spoke a little bit about firmware last time, so we talked about kind of that middleman. Firmware is kind of the best of both worlds. We get the hardware aspect with the software flexibility. We did talk about firmware last time, right? Okay. So what's the perk of hardware? Good. Fast. Speed. That's it. Software where we know that when we write our Java program or our C# program or whatever, that there's a whole bunch of layers of crap that happen between us writing that stuff in a text file and it ultimately executing on the CPU. It has to go through all sorts of different conversions and reorganizations, and then there's a lot of stuff, a lot of steps in there. It's convenient for us because we don't have to speak binary gibberish to the computer, but it's still a lot of steps. So we can make the assumption, if we were wondering which is faster, the software that we wrote with all the translations it has to go through, or electricity running through hardware, we'd probably say the hardware is faster, right? So the perk of hardware is that it's fast. What's the downside of hardware? Okay, more permanent, fair. Why is that a downside?
You wear out materials if you have to, like you said, it's a lot harder to change circuits.
Okay, I think that's the real punchline. It's you make a mistake, you're either starting over or it's a headache to not start over. You're getting the soldering iron out and melting stuff and that kind of stuff. I think we looked at an Arduino last time, right? Did we look at a breadboard last time?
Mentioned it. We talked about it.
Okay, well, let me just show you, just to fill in that gap. Breadboard. All right, so this guy, let me find a solder breadboard first. These guys. So this would be our historical breadboard. All right, so it's something that has, so this is a piece of silicon for a circuit board. It's non-conductive, so that's why. So the whole thing isn't just electricity, and then some bunch of holes drilled in, and each hole has conductive material. All right, and the idea is you would solder wires, and maybe you'd have a wire go from here to here, and there might be a component here that also powers it, and somewhere here you'd have a battery off the side of it that would plug into this to provide power to the breadboard, and it provides power on the rows and columns, and all that stuff to get it to make your stuff work. Well, this is a solderable breadboard, which means that you drip molten metal onto this thing, let it cool off so it solidifies stuff, and now that's effectively permanent, right? You know, it's technically you can get it off if you just heat it up again, but it's not easily changeable. You are going to have issues. So the upgrade to that was this idea of a, you know, solder-free breadboard. So with this, inside of each of these little holes is, you know, there's a metallic, almost like a clip. So when you push a wire into it, it almost just kind of has enough resistance where it just holds it there. I mean, you could pull it out, but you know, it wouldn't just slip out on its own. You have to kind of be a little bit careful. You provide the power over here, so it's a lot easier to build prototypes. It's less permanent. You don't have to work with melting metal and making sure it's in the right spot. I mean, if we go back to this guy, if you put too big of a gob of metal here and it all of a sudden touches this next guy next to it, now you've done something and maybe you didn't intend. Make sense? All right, so working with hardware directly can be, it's delicate work. All right, working with a solderless breadboard like this, you know, if you need to make a change, you're kind of getting in there with all the wires, and you know, depending on how big your hands are, how steady your hands are, you might, you know, you change one thing and you knock 3 other wires out, and you're like, oh well, where did those go? You know, that type of stuff. So certainly not something that I'm made for, because I have big hands and tremors. So so a good funny video would be fun with soldering irons for me. That would just have melted metal all over the place, and you know, that's as steady as it gets.
Drink too much coffee?
No, I just have it's called an essential tremor. It's the thing. Probably,
Essential?
yeah, that's what it's called. It's a neurological something. I mean, it just happens.
Just holding it still, I think.
Yeah, I did. Yeah, this one's good. Ish. A lot better. This one's better.
Videos on Facebook where they made like utensils and stuff that
Yeah, for people with tremors.
That's really cool.
Yeah, where like the spoon is like it's on the spoon. Yeah, that's what happens. It's when I try to do fine motor skills, I end up like knocking stuff off forks and stuff like that. But it doesn't impact my golf game. It's weird. Yeah, it's really for just real fine motor stuff. But whatever. There's worse things to have, I suppose. But yeah, soldering really isn't my thing due to this. Because I would be basically just spilling solder all over the place, including on myself, and none of my circuits would work, is what it would come down to. So in any case, we kind of have this idea of a solderless breadboard that allows us to create hardware prototypes without using solder. So that would be a little bit easier for me, but you know, if I try to grab the end of one wire, well, I'm going to pull it out without really thinking about it, because my hand's bouncing all over the place. So also not my thing, but still more permanent than software. Software, you backspace a couple times, we're right back, you know, we make our fix and compile, we're back in business. So these guys are more delicate. So that's kind of where firmware came in, where we can have the benefits of the hardware fast with the bug fixability, you know, the convenience of the software in the middle. So now we said that, so you said hardware is permanent, and we were talking about it being a downside, that the permanence of hardware is a downside. And that's because if you have a problem with it, changing it is a headache. Anywhere from a small inconvenience to possibly a major headache. Start over or something like that, depending on the complexity of it. Okay. So if we say hardware, pros, it's fast. Cons, permanent. All right, so fair enough. Okay, so when then would we decide that using hardware is an okay idea? I mean, clearly we have hardware, right? Where many of us are sitting here with laptops running in front of us, so that's got certainly hardware inside of it, right? All right, so most of us have smartphones or cell phones of some description. That's hardware. So when do we make that choice? When do we decide we're going to do something in hardware versus in software? Is it always a speed decision?
It's something that's going to be used like almost all the time, consistently by any system.
Okay. Can you give me an example Probably not, I'm guessing.
Basic operations. You're obviously going to need like adding, subtracting, all that stuff. Hardware.
Okay, so you're thinking more of like the actual circuits on the CPU. Okay, I'm thinking more like real life solutions. Like when would you write a program to solve a problem versus build a prototype to solve a problem?
I think you'd always start with the software.
Okay.
Why would you immediately start doing hardware? You test the idea.
Well, some things there aren't equivalents. So, let's say that you are taking the temperature of outside. You want to have a Bluetooth-based thing that reports back to some website or something like that, the current outdoor air temperature. Well, so you can write this in software, but at some point you're going to need to have the ability to measure temperature. Okay, and you can go down the path. You could be, working in software, as much of the time as you possibly can. But at some point, you're going to need an instrument that can tell you the temperature, and that becomes a hardware-based thing. Unless you just use an API and contact the Weather Channel. It's like, well, I don't really want to take the temperature here. I want to take the temperature near here. So you give it your current zip code or GPS location using location services or something, and you ask the Weather Channel for the current temperature, and you display it, and didn't do it with any hardware. Well, that Weather Channel probably had some hardware somewhere along the lines there. So at some point, we have physical ways of measuring things. We have tools that are going to kind of measure the world outside. So sometimes it's out of necessity. What else? When we think about the things in our life that are hardware based, is it usually kind of portable things that we need to be able to carry around with us? It's a random Pennsylvania number. A lot of times we're thinking about it in things that they don't exist inside of our computer. They exist as widgets that we carry through life with us, right? Even our, your keys to a lot of your cars. You don't. It's not that common anymore to be able to walk up and actually manually unlock your door. You pushed a couple little buttons, right? I for some reason refuse to get into my car unless it's already running. So I have one of those auto start things. So as soon as I'm within range, I get it on so the air conditioning has time to cool off. That way I'm 100% of the time comfortable. So first world problems, right? So, in any case, we don't always choose hardware because of its speed. Sometimes we choose hardware because of its necessity. It's almost like how many of you have seen the TV show? I mean, I'm sure a few of you, but maybe you've heard of it, the $1 Million Man. You heard that show? So, kind of I think it's an augmentation thing, or RoboCop. The movie's RoboCop. So we had a dude, should have died. They turned him into a robot, so he's half dude, half robot, and that's, kind of the best of both worlds. So sometimes we have software because there's a convenience there, or there are things that we can write in software without it being a problem, and then we have hardware out of necessity. All right, so that's where the firmware thing comes in, where we can we can have the permanent aspects of it while still having the convenience of some of the logic happening in software where it can maybe make sense. Okay, so let's go back to here. Okay, so as you read through this assembly language stuff, why write something in assembly language? So you guys are already working Java and stuff like that. Go ahead.
Takes less memory.
Okay, why does it take less memory?
Goes to ones and zeros, takes up less space.
Okay. When you write something in Java, doesn't it ultimately turn into assembly language at a point? I mean, we talked over here that you write your Java program and there's many, many, many levels and translations, and eventually it's got to hit something that runs on the CPU. And that's a low-level language where we're talking one-to-one with the CPU.
You don't have to translate it though.
Okay, so there's no translation.
Yeah.
Why does that lead to less memory?
Because you don't have to have instructions for how to translate.
Okay, so I could maybe see saying that there's less total memory used in the process, but once you compile a Java program, now that memory is not being used. But could we make an argument that a running program in assembly could take up less of a memory footprint than the equivalent program that was generated by a Java compiler, for example. Okay, why is that?
More direct and you can optimize it to run faster and with less memory than if you had to translate it. You don't know exactly how the translation's written.
That's it, yeah. So the idea is that, for instance, for those of you who, and this goes back to an old conversation we would have had a while ago about, I had it in 250 today with the why languages like Java, which are based on C, have so many different ways of representing whole numbers. Bytes, shorts, ints, longs. It's the whole Y2K thing. Memory used to be really expensive, blah, blah, blah. So historically, somebody who was writing a program in C maybe would have chosen to use a byte primitive type, which can only hold 8 bits. So negative 128 to positive 127. Again, that's the 2's complement thing. So 7 ones is 127. The negative of that is negative 128 if you do the 2's complement of that. So that's your range. Now, because of the carry bit. So punchline here is that historically, a programmer maybe wrote more memory efficient code in a high level language like Java or C. Today, when you're writing your Java code, how many of you have used a byte when using Java? How many of you have used a short? By accident, you were copying something off the Google. So I stole an old C program and I converted it to Java, and the guy used the word short in there. Okay, we use ints, right? All over the place, we use integers. So left and right, we're using int. Every now and then, we'll throw a long in there if in the event that we need to hold the number bigger than 2 billion, right? And worst case, if we have to hold a number bigger than 4 quintillion. For actually, it's 16 quintillion for a long. It's plus or minus 2 to the 63rd power. So it's 2 that. So I guess, okay, it's 9 quintillion. Big number, but not infinite. It's a big number. All right, so if we need something larger than that, we go to one of our object types like big integer or something like that. So today, if you're primarily using 32-bit variable types, like an int in Java, to hold a value that may not take anywhere near 32 bits of actual space. If we did that at the assembly language level, we could be much more direct about how we want to store that value. We would be explicit about saying, here's the value, and I want to store it in a register that is built to hold this much stuff. Okay, tell me about registers. What is a hardware register? Go ahead.
Holds a small amount of data, like the address.
Small amount of data like the address. I have a feeling you do know what it is, but that kind of sounds made up.
It's like one of the fastest ways of holding data.
Okay, so it's memory. It's a memory thing, right? Okay, it's a memory thing, and it's fast.
Yes.
All right, fair enough. So we're kind of working with this idea of hardware is fast. At some point, we spent a while in the grad class the other night talking about this whole concept of what fast means, but we're not going to really have that discussion here because they're talking about a bunch of different stuff in there. But we'll say hardware is faster than software, and we're going to say that's fair for us. All right, so it's fast, and a register is memory. Now, are registers, relatively speaking, big amounts of memory or small amounts of memory? Tiny, by our standards, right? We think about the memory that's in our computers. So I have 16 gigs of RAM here. I'm guessing there's probably some other 16s. I know that we have a 12 over there. There's probably 8 gigs of RAM in some of these machines, 4 gigs of RAM. Okay, so how many of you have 8 gigs of RAM in your computer? kind of your commonish, decent computer today is 8 gigs of RAM. All right, so how many bits are in 8 gigs of RAM?
Hey, I got a question for you. So I'm reading this thing, and they tell me there's 9 bits in a byte.
Reading whose thing?
This assembly introduction thing says there's 9 bits in a byte.
They're probably talking about the carry bit.
I thought they were talking.
They were saying that-
parity.
Parity bit, yeah. So this is a more of an assembly language discussion.
Okay.
So a byte is 8 bits. A byte by definition is 8 bits. But in assembly language, we need to be able to handle transitions between multiple bytes because if we have a 4-byte register or a word register, so that would be 32 bits. We need to be able to handle that transition between those partial bytes of it, and that's where we have these extra little registers, placeholders. Like if this flag was set, that means that we go here. It tells us kind of the story of where the numbers went. So that's where extra bits come in when we start using the actual registers. But a byte is 8 bits, 100% of the time. It probably goes into the same category as the reverse, a little bit misworded or something like that. Okay, so hardware registers are very fast and very small memory locations, typically located very close to the CPU. All right, so now we mentioned if our average computer today has 8 gigabytes, and let's say in a 32-bit processor, some of our processors today are 64-bit processors, actually most of them today are 64-bit processors, an average register size might be 64 bits, okay? So we'll use that. It'll make this number seem less scary, but it'll still be scary enough. All right, so let's say we have a 64-bit register. How many 64-bit chunks are there in 8 gigabytes of RAM? So we start off by saying how many bits are in 8 gigabytes. How do we calculate that? So 8 times 1024 times 1024. So this takes us to megabytes, to kilobytes, to bytes, to bits. All right, so what is that? 68,719,476,736 bits divided by 64. So 1,073,741,824. So you can hold over 1 billion 64-bit hardware registers in your 8 gigs of RAM for the equivalent amount of space. Okay, how much does 8 gigs of RAM cost if you were to buy 8 gigs of RAM for your laptop? $30, something like that, $40. Not a lot, right? How much does a CPU cost, relatively speaking? More, right? Okay. And in that CPU, we have a collection of hardware registers. So how many hardware registers might we have in a CPU? It kind of depends on the class CPU, whether it's an ARM processor on like a Raspberry Pi or a cell phone, or it's a Intel-based processor, and then which architecture for the Intel-based processor. But maybe we say there's 20-ish. Throw it out there, 20-ish on your average CPU number of hardware registers. All right, so that means that, and if all of those are 64 bits, which they're not, only a small percentage of the processors are going to be maximum size. But even if we give them the benefit of the doubt, and we say we have 20 times 64, that's 1,280 bits of total memory on that $300 processor. That's not a lot, right? So punchline here is obviously the CPU, the that collection of circuits has value associated with it, right? So that's part of that $300. But chances are register-based memory is far, far, far more expensive than the system RAM that we're talking about in our laptops. It's also far, 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 far faster. Make sense? All right. So we have these hardware registers. These guys are considered to be really, 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 really fast. Let's go. So now when we're dealing with, the conversation we're having deals with how can we make an assembly program more memory efficient than a Java program. It's because when we move values around in assembly, even though we're having to be very granular about it, we take one tiny little baby step at a time when we deal with assembly language. We're being targeted about where we put values, and we put values in certain registers they're the only place we can put a value, because certain registers have a kind of a purpose, at least as it relates to the operating system that it's running on, and we'll talk about that here in a second, just to kind of put the picture together. But we can be much more targeted about the exact memory location that we place a value in terms of how much of that memory location this value fills, rather than relying on, as you pointed out, we don't have control over that compiler. So we don't know what Java is going to do with our integer value that holds the number 5. Okay? Chances are it's going to go and find a giant plot of land, okay, and throw this little tiny value in it and say, we're good. Okay, we're good. So in the end, you might have something that's functionally accurate but has a much larger memory footprint that comes out of Java. Now, realistically for us, is that too much of a problem today? Significantly less of a problem today than it would have been in the early 70s.
That would affect speed though, where it puts the bit back.
Well, okay, so yes, it would, but would it affect speed in a way that was perceivable by us is the bigger question. And well, it really depends. It depends on what the application is, right? If you have if you have a timer, let's say, so you can have a mechanical timer, or you can have a software timer on your phone or something like that you're using. Well, technically something shouldn't take more than 1 second if our granularity is 1 second timer, right? If we're not looking at fractions of a second. Okay, we have 1 second timer. As long as nothing takes over 1 second to do the stuff in the middle, doesn't matter whether it was done in hardware or software, even if the software was way slower, because we won't recognize that as a problem. Now, what's some examples of things where speed does make a difference? Can we at least all accept that there are definitely applications where
Gaming, that wasn't a huge thing, that like even after assembly stopped being popular, a lot of game developers were still making their games in assembly.
aspects of their games? Yeah, even today, there are aspects of some games that need to be very fast. And really, the places where we see that most often is so consider from your programming experience that you've probably run into situations before where you have an if-else statement or something like that, and you happen to know that this chunk of code will never occur. Like, look, I know the data this guy is going to be getting. This isn't going to happen, okay? But Java forces you to write it, or it won't compile, right? Because it's part of the structure of an if-else statement or something like that. Even though you know for a fact this is literally a waste of time. So that's going to produce the equivalent assembly language with the equivalent lines of code, with the equivalent logic. Really what it usually comes down to is the equivalent number of questions that need to be asked. So if we kind of go back to that very first thing when we first start talking about programming, how do human beings solve problems? Memory, asking questions, and repetition. The more questions we ask, the less efficient it is, right? That's little kids they're cute for 15 minutes, and then when they ask their 4,000th question, they're like, yeah, okay, I've had enough of this. You go duct tape them to a chair somewhere. But we don't do that anymore because that's cruel. So now we just put them in front of a video game system. Same thing, but it's way less cruel. So giving them an iPad is equivalent to duct taping them to a chair. It doesn't look the same, but it is the same. So they're not leaving that chair. All right, so punchline is that the more questions we ask, the more time it takes. Okay? Whether or not we perceive it being an issue is a whole different question. So when we come down to like video games today, if there's a section of a video game that really needs to be fast, okay, there's a whole lot of logic that's occurring in there where there's a lot of decision making in this one section of the game, and you have to write that in a high level language, probably C++ or C# or something like that, and you have to write it in a high level language, you're going to be playing by the same rules as you're playing like in Java, where the language, the high level language might dictate that you have to have a whole lot of extra, mumbo jumbo in there that as a human being will never get executed based on the nature of the data you're working with. But C, C++, whatever, is still going to force you to do it. You might then decide to go in and edit that code at the assembly level and say, okay, well, here was the code that was generated by my compiler, okay, by my C compiler. Here's the assembly code. Most of this is a waste. So what I'm going to do is I'm going to take a majority of this out, and now we have this. This is the actual code I want. Very few questions being asked in here because I know the nature of the data. And the nature of the data is going to say, go through this as streamlined as you possibly can. Okay? So this is typically where we would have assembly language still existing in video games today. It's also why sometimes you're playing a game and then it just goes away, it just crashes. Because sometimes that nature of the data, for whatever reason, changed. Corrupt memory, something like that. Most of the time, video games do not crash gracefully. Fair enough? Okay. Usually your whole screen kind of turns a weird color. At some level, Windows finally gets its act together and puts up some thing that says this program has stopped responding. I mean, that happened, milliseconds ago. But but I'm letting you know about it now. But you probably already noticed because you haven't been playing for a while. it's been shut down. But they don't crash that gracefully. All right. Part of that is because they didn't put extra stuff in there to handle those things because they would rather it crash sometimes and be fast most of the time than, let's say, rarely crash but always be sluggish. Kind of make sense? Some of the decision-making type stuff. Okay, so let's kind of go back over here just to see what you guys looked into. Okay, so the question I kind of asked is, when might assembly language be used? So you used gaming as an example, not necessarily life and death, but realistically is a reasonable enough example. There are some things that we want to streamline as much as we can, and relying on a high-level language isn't going to allow us to do that. Fair enough. Okay. So you guys looked at this stuff a little bit. This is just kind of multiples of bytes. Now some of our hardware can hold 1 megabyte at a time. Specifically, we're dealing with like the various caches on your CPU when it comes to those things. So if we think about our CPU, this guy's a collection of circuits. It's also a collection of memory locations. Okay, and we already talked about registers as being some of those memory locations, super fast. Then we have various types of cache. So this is slightly slower memory. And these guys typically have names, L1, L2, L3 cache, that kind of stuff. We're mostly interested in registers in here, but just to kind of give you an idea, the farther you get away from the CPU, the slower the memory gets. But relative to human beings, memory is fast. So, your 8 gigabytes of memory in your laptop is fast. It's fast memory compared to your hard drive. Okay, way faster. So, the hard drive is like me, and the memory is like Usain Bolt. Okay, but actually, that's not even a good example. Hard drive is me, and the memory is like the space shuttle. That's probably a significantly closer example. It's probably still an understatement. I don't know. I think I'm just that slow. Hey. All right. So in any case, this is kind of the stuff that makes up our our CPU. All right, and as we get farther away from the CPU, we start having the ability to store larger chunks of memory. We get very far away from the CPU. We start thinking about our system memory. We have 8 gigabytes. That's a big bucket to hold stuff. Okay, that's not going to fit on our CPU, and it's going to take up way too much space, and we'll have to reduce our number of magic tricks a lot. All right, so you looked at the binary number system quite a bit. We've talked about that a lot. Okay, all the classes you've had with me, I've always done conversion stuff. So, converting between binary numbers to decimal numbers, all that stuff is absolutely vital. I mean, you're going to need it when you go into Culver's. You order, sometimes they give you your change in binary. So that doesn't happen to you in Culver's? What Culver's are you going to?
I pay with a credit card.
Oh, that makes sense. Say, well, if you do the Bitcoin thing, it's they just start throwing binary stuff at you, and then you try to get the good deal on the coupons, so you start throwing hex back at them. It's a thing. Yep, it's a thing. Okay, so let me just keep going. So we talked about binary arithmetic a little bit. You read about that stuff. Okay, so now we start thinking about actual instructions and how numbers are stored inside of some of our hardware registers. So with Intel-based machines, and one of the reasons that, well, a couple of reasons we are going to use Intel assembly in here. One is what the book does. 2, it's going to be a pretty general purpose and you'll be able to apply it to anything. 3, it's a better time to use Intel assembly than ever over the, rather compared to history, because now our modern computers all use Intel. So whether you're on a Mac or a PC, the processor is an Intel processor. All right, so the instructions that processor understands are identical instructions. All right, let me just quickly scroll through here. I want to see how far. Oh, this is as far as it took you, right here? Is this all you guys read to, right here? Okay, so I'm going to just pause that for a second and let me use this as an example. Let's just go right here with it. Intel assembly, Mac versus PC. Now, historically, if you were, how many of you have been Mac users for a long time? Back before Macs had Intel as a processor. Okay, so this becomes a Trivial Pursuit question then. Okay, what kinds of processors did Macintosh computers use before they used Intel processors? Go ahead. PowerPC processors. Okay, so this was a processor made by IBM, and it was known as a reduced instruction set processor. Okay, a RISC processor. Reduced instruction set. All right, so now, what's the benefit of having a reduced instruction set versus an expanded instruction set? So we're going to say Intel has a whole bunch of instructions. Let's just, to have the numbers be easy, let's say that the number of magic tricks that an Intel processor understands is twice as many as the number of magic tricks that a PowerPC understood. Okay, those numbers are likely humongously off. Okay, probably it's more than twice, to be honest. But let's just say it's twice. What would the advantage be of having fewer instructions that the CPU understands versus having more instructions that the CPU can understand?
Faster, because I wouldn't have to go through as many.
Okay, let me ask it a different way so I get less stupid answers. I'm always looking for that opportunity. Hold on, I'm getting more phone calls with that. All right, so how many of you are like pretty handy around the house, building stuff, things like that? Well, you're from Indiana, of course. All right, anybody else pretty handy? Okay, so we're going to give you the little budget pleaser toolkit. All right, so we're going to go to Home Depot. It's the $9.99, household toolkit. right? We're going to give you the $300, every tool known to, toolkit. You have everything you need, okay? So now we're going to give you guys an equivalent job. Now, are there going to be some jobs that I can give both of you where you're going to probably use the same tools? You're going to be using a small subset of the tools you have available to you, and you might be using a large subset or all of the tools I gave to you, but you can solve those problems. Now, when would it be advantageous for you to have more tools?
Probably for a bigger job.
Okay. Now, can you give me an example when you have a bigger job? Let me give you some more constraints here. Do jobs exist where he could accomplish it with his tool set, but he might not always have the exact right tool for the job? Where you could also accomplish it, and you have the exact tool you need. He might have to MacGyver it sometimes, right? Okay, but he could do it. So certainly there are going to be times where you being able to do it with the correct tool is going to be advantageous, right? Can you give me an example where it maybe wouldn't be advantageous to always have the correct tools? What's the cost of having this gigantic toolbox with 4,000 tools in it? More space, heavy to carry. All right, so now when we think about it, take it back to the computer side of things, each one of those tools gives off heat. All right, so now you have this giant box of tools it's just radiating heat. Okay, you're carrying around a bag of fire is what you're doing. Okay, where you have some heat coming off of it too, but since you have far fewer tools, there's far less heat, which means there's far less stuff that you have to protect, right? You're gonna have to wear fire retardant gloves, okay? Where he could probably just use a couple of folded up napkins to to kind of work with it. All right, so we start to see some of the comparisons here. So reduced instruction set maybe doesn't always give you the perfect tool for some of the jobs, but it has some advantages. Less heat, less stuff that we have to deal with. More of that space can be used for things like memory and stuff like that. So if we say that a PowerPC processor and an Intel processor, let's just as an example here, let's say they're physically the same size. And we've already said here that a CPU is a collection of circuits. Okay, so since a CPU is a collection of circuits, if they're physically the same size and the PowerPC has less circuits on it than the Intel processor, that means he has either A, more room to put memory, if he chose to go that direction, certainly has more room to put heat dissipation type things, so he's probably going to be able to keep the CPU at a cooler clock speed, and generally speaking, when we talk about electricity, heat is the enemy. All right, anything with electricity, heat's the enemy, so we need to be able to dissipate that heat, otherwise bad things happen. All right, was it in here or was it in my grad class at the story from my grad class? Yeah, so I had a buddy of mine in undergrad. This was back in the days where overclocking processors was a very new thing. Today you get a motherboard and it's everything is in software for overclocking, right? Now this is in the day where you had jumpers and then you would solder a wire between here and here so that whatever special checks that made it not overclock didn't get checked, that kind of stuff. So he had overclocked, I think it was a 200 megahertz Intel Celeron processor. He overclocked that to something like 1.2 gigahertz. All right, and this was back when anything with the word gigahertz after it didn't exist. Okay, that's just 1.2 gigahertz doesn't sound like anything today, right? Okay, that was space flight back then. All right, so so it's 4 a.m. So I almost always had my door open to my room because I was always in there programming. I was ultimate nerd. So he comes down at 4 a.m. He says, guy, basically, he was kind of calm. He was probably high. But, he's I need your help. I have a problem. So I come out of the door. So I'm right off the elevator by my dorm room was there. He was all the way at the other end of the hall. by looking down the hall, so this is Christian worldview here, it looked like I was looking at the gates of hell. Okay, there are flames billowing out of it. His entire dorm room is on fire. Okay, now this isn't like a small little like oh, the popcorn caught fire. Oh. No, his room is on fire. Okay, bed gone, curtains gone, everything gone. Okay, his room is on fire. He was sleeping in there. Like not that long before that.
And his first thought was to come knock on your door.
Yeah. Yeah. So And even now I kind of think back. I mean, he had to have only been out of his room for 45 seconds. I can't imagine what happened then. How it could have looked that much better 45 seconds before that, and he was still in there. Okay, but in any case, heat is the enemy. Okay, so he had overclocked this processor, and he basically just had like a fan, like a normal desk fan, just blowing into the side of the case. Kind of an interesting.
So wait, how long did he have that functioning like that, or was that the night he did it?
At least that day. But I don't know. Maybe he didn't have it on a bunch, or maybe he took it up to even higher speed. I don't know. So how many of you have built your own computer before? All right. How many of you have dabbled with things like liquid cooling and that kind of stuff? All right. So, so the cooler you can get it to run, the higher, the higher processing power you get because, again, heat's the enemy. A common misconception with computers is, my friend here had this misconception, is you take the side of the case off and that allows more heat to get out, to escape. You get a fan that blew it around. In almost every circumstance, that machine will run hotter with the side of the case off. The reason is the fans in those cases, you see like the square case fans, they're in the position they're in to create a circular airflow that vents out the back of the computer. The second you open the side, you lose some of that aerodynamics. So kind of just an interesting thing, I guess. So taking the side off the case doesn't necessarily make it cooler. Probably makes it warmer, or at least doesn't help, let's say. Okay, so let's see, where was I going with that? Heat is the, RISC versus Intel. Okay, so we have our Intel processor, we have our RISC processor. All right, so a RISC processor, we're going to be running a lot cooler. Intel processor, probably going to be running a lot hotter, or at the very least, now we have a necessity for larger fans, whatever. We're going to have to deal with the heat problem at a more serious level on the Intel processor, with the bigger bag of tools over here. All right, so right off the bat, we can kind of see pros and cons, right? He's got the little bag of tools, so he's going to be pretty mobile, able to carry it from place to place without getting tired. It's not too hot, but he also has a reduced, capability. The hope is he has all the tools that he'll need to solve all problems, but what is that minimal? So what a reduced instruction set was going for is what is the minimal collection of tools that are needed to solve general computer problems? All right, so if we were going to kind of throw that out here, what is the minimal collection of, I'm going to use my phrase, magic tricks, needed to solve common, well, let's call it general computer problems? And likely that was an evolving thing, right? You kind of make your best guess at it first, and so he kind of puts together his toolkit, and he starts doing some odd and end jobs, and then he realizes, what? Even though I've been kind of able to MacGyver this a little bit, it would really be helpful if I added one additional wrench to this bag. I'm kind of needing this pretty often, and what I'm having to do to solve that problem is just doesn't seem efficient. All right, so. You get a couple more instructions thrown in there, a little bit more heat, but as long as, you made an okay enough guess to begin with, the hope is you're in decent shape. All right. Okay. Now, back over on her side, she's got her toolbox is on wheels. All right, she's dragging this thing around. I mean, it just weighs a lot. All right. Sometimes her biggest problem is deciding which of the correct tools to use for a particular problem because she's got everything. It's like, well, am I going to use the bandsaw, or am I just going to use a hacksaw to, whatever, you have options. You can pull it off in a whole bunch of different ways. So now, sitting at this level right now, who are we betting on long term? Okay, is that because Intel seems to be the winner? There's actually some that's not entirely true that Intel's the winner. We'll circle back on that here in a second. But okay, so you're going to bet on the Intel over here. Why?
You don't have to deal with having to apply more tools for the problem you already have.
Okay.
So therefore, in the long term, when stuff's improving, it's already at that level. It doesn't have to improve the process itself.
Okay, so from a human perspective, so again, I want to drag this away from computers as much as I can, then we'll push it back. So you feel that as long as you can come up with convenient ways to cool the tools and to move with the tools, travel with the tools, that he's going to more often than not run into kind of coming up with complex solutions to what should be easier problems, right? When you just don't have the right tool for the job. I can't tell you how many times that has happened working on a 1978 boat in my garage. Nothing is the right tool for a 1978 engine. But you know what works really well for moving 1978 Chrysler engines? Students. Oh yeah, I have video of, were you there for that one, Curcio? No, you moved the hot tub. Students are also good for moving hot tubs. Yeah, we got a video of, I think, like 20 computer science students deadlifting a hot tub straight up and then moving it to the back of a pickup truck. Those are the good old days. Yeah, I'll come up with something for this semester. Yeah, the night that I think Abe Rody, the patriarch, he helped move the motor. He almost died that night.
How come I didn't hear about this?
He took all the way to that motor at some point because, I don't know, Blade got scared, and Blade's a Chinese grad student. And he flipped out. He couldn't carry it anymore. So at some point, Abe had a 500-pound motor just on him. And I think he died at some point. So I mean, I don't even know how something horrible didn't happen, to be honest. But it all worked out, and now my engine works. So I got what I needed out of it. I mean, sometimes there's casualties. All right, so you're betting that his toolbox is going to be inconvenient too often. He just has to come up with complicated solutions to things that just shouldn't be that complicated. And it's going to be easier to come up with overarching solutions for heat dissipation and stuff like that, with the trade-off being that you always have the right tool for the job. It's a fair enough assessment. I mean, that's kind of seems reasonable to human beings, right? Okay, and reality would indicate as eventually Apple switched to Intel for various reasons. I'm sure part of it was cost. The cost for PowerPC processors was substantially higher than it was for Intel. PC market is still significantly larger than the Macintosh market, right? Apple makes up for it kind of in mobile device thing, and Apple's market share in the personal computer area is larger now than it's ever been, but it's not the PC market. The PC market's huge, right? So Intel has been creating things in bulk for that industry for a long time. So it would be reasonable to assume that it would be more cost effective to buy Intel chips than to buy PowerPC chips. And to exacerbate that issue, IBM was having issues producing the PowerPC chips. They had a high failure rate off the assembly line. They weren't necessarily putting out chips that didn't work. It was they would try to create 100 chips, and out of that, 20 would work. So they could only ship 20 out of the effort of 100. So it made it even worse, what I'm saying. So the cost to produce was even higher. So in any case, and there was, I'm sure, other dynamics. This all happened when Steve Jobs came back to Apple, and Apple was kind of failing as a company, so they had to pivot and make some new decisions and hope that those worked out, and it did. So punchline is that now we have both platforms on Intel. So we might say that Intel won. How many of you have smartphones? All right, how many of you have iPhone of some sort? Okay, how many of you have Android of some sort? Anybody have something else? A Windows phone? You have a Windows phone? Oh, is Vietnam?
No, at home.
Huh?
At home.
Well, no, I didn't mean was it in Vietnam. I mean, did you get it in Vietnam?
Yeah.
Yeah, because that's what they sell there. For the record, I'm good friends with him too, so I'm always making fun of him about it. He's you're not related to old Alex, but you're friends with old Alex.
I'm a bad friend.
Best friends with old Alex.
I'm sorry.
Old Alex was one of our undergrad students who's now in our grad program, also from Vietnam. And his name is not Alex.
It is now.
Oh yeah, he did. He said he legally changed it.
No way, he did not.
Yeah,
That's awesome.
nobody's gonna believe that. Yeah.
Like he actually did it, or he just said it?
No, he said he did. I think he was true. I think he was telling the truth. Okay. So in any case, so we all have these smart devices, iPhones, Android phones, Windows Mobile, whatever. What kind of processors are in our phones? ARM processors. What does the R stand for in ARM processors?
Awesome.
No, not the A. The R.
Oh, the R.
What is the R? What is the R? What does the R stand for in ARM processors? Yeah, ARM processors are reduced instruction set architectures. So we might say that reduced instruction set, that idea was maybe a little ahead of its time, right? I mean, we can look at all sorts of examples in the computer hardware industry where this has happened. How many of you in your personal computer have an AMD processor? Okay. Far fewer than historically have had that, right? Most of us had Intel processors. Now AMD is Intel compatible. They have a couple little bells and whistles. They say, well, we're better than Intel here, and Intel says we're better than them here, and it's like the hyper-threading versus whatever AMD's made-up version of that is, but whatever, doesn't matter. Okay? There was once upon a time, that was a real battle. I mean, they had 50% market share, each of them. You know, who was better, AMD or Intel? Well, so we'll go back to him. Who won? Well, Intel. Clearly, we only had two people in class raise their hand, and I'm pretty sure one of them was lying about having AMD. Why? Why did AMD lose that battle? What decision did they make that was ahead of its time that caused them to lose that battle?
64-bit.
Yeah.
They switched to 64-bit and Intel.
Yeah. So AMD released a 64-bit processor called the AMD 64.
Cars are awesome, bro.
Okay. So they released a 64-bit processor. Now the idea was 64-bit software wasn't necessarily readily available, right? So they kind of had to make it work two ways. So this guy was backwards compatible with translation for 32-bit. All right, so if you could run it in 64 bits, you were golden. But if you had to run it in 32 bits, you were effectively, I don't know, let's take a Ferrari. Okay, we're going to do a Ferrari, and we're never going to take it above 40 miles an hour. Okay. Make sense? That's not a problem for me because I don't physically get into a Ferrari. Yeah, I was at a car show one time, and they had even a Porsche there. And even once I got in, my head was I was above the windshield.
Oh, you were in between, you were above it?
Yeah, because so I'm tall anyways, but I'm from torso up, I'm like over 7 feet tall. Because I only have like a 30.5-inch inseam. My legs are relatively short, so I'm like almost 6'5". So I'm relatively tall that way. And I didn't come anywhere close to fitting in this thing. I was like, and then you have I know I seem petite, but in real life I'm not. Okay, it's all an illusion. It's optical from the lighting. And okay, so for your homework assignment, write a 2 to 3 page paper discussing why AMD was ahead of its time with the 64-bit processor. Specifically, discuss Intel's decisions related to the Itanium. It's called the Itanium. Itanium processor. Make sense? Okay, so that's going to be due on Tuesday. On top of that, go into the textbook and let's go up to section 1.6 in chapter 1. So 1.1 to 1.6 in chapter 1, do the reading and do the little exercises that come with it. There's like little, short quizzes, like 4-question quizzes. Not a graded activity, but it's an assessment activity, so I'll be able to see that you completed those things. All right? Questions, comments, concerns, bribes. All right, I'll see everybody on Tuesday. No class Monday because it's Labor Day.
Could you put the assignment on the paper system?
I'm putting it up right now. Yeah. That assignment that I just gave will be in a Dropbox on Blackboard in a minute and a half.